Hello, this is Jack Jackson. We're going to continue our series of videos on applications of integration by looking at some motion problems in this particular video. So in this particular one, we have a graph here, and this graph is going to represent the velocity of a bicyclist. So the bicyclist is pedaling along a straight road with velocity v in miles per hour, given by this graph, where the graph is velocity as a function of time since starting her trip in hours. And suppose that the cyclist starts 5 miles away from the lake, and that positive velocities take her toward the lake and negative velocities take her away from the lake. So see if we can make sense of what's meant by this graph. Okay, so here's the basic picture down here. Here we have the lake. Here's the long straight road. She's going to start 5 miles from the lake. Going toward the lake is positive and negative is away from the lake. So actually, if 0 are the coordinates where the road hits the lake, then negative 5 are the coordinates of where she starts. Okay, so what happens here? She starts with a positive velocity, so she's going to the right on this graph, so she starts going to the right. She speeds up, going faster and faster. She sort of maxes out locally the speed toward the lake here, and then she comes back and slows down. Right here, 20 minutes into her trip, 1/3 of the way for her 1-hour trip, she turns around and starts going backwards. And then she comes in here somewhere perhaps, turns around and goes backwards the other way. At some point in here, I don't know where it is, maybe it's around 0.5 something, say somewhere in here, this area is the same as that area, and she is back where she started, and then she continues to go further away. Her fastest speed is actually right here, where the velocity, absolute value of the velocity is the biggest, which is this. It's about negative 3 miles per hour, which happens here at about 0.74 hours, or about 0.75, 3/4 of an hour would be 45 minutes. Maybe about 43 or 44 minutes into her trip is when she's going the fastest, and this is actually going away from the lake back to the left, and she's going fastest toward the lake here about at this point right here about 0.15. By the way, each one of these each one of these is 0.5 hours for the grid lines. 0.05 hours times 60 minutes means the grid lines are about 3-minute intervals. Okay. Notice that the distance here is the horizontal distance on the graph is actually representing time and hours, and the vertical distance is representing velocity of miles per hour. So in this case, areas represent miles per hour times hours equals miles. So areas represent distances traveled. So this area right here represents the area she traveled toward the lake, and this area represents the distance she traveled away from the lake. Notice there's more area here below the x-axis than there is above, so the net result, she ends up further away, further to the left of her original position, which puts her further away from the lake than she was to begin with. Also, however, remember, she started at a coordinate of -5 in this coordinate system. Okay, so if this area right here were exactly 5, then that meant she would go exactly to the lake when she turned around and come back. If this area were less than 5, then she goes that distance to the left, to the right, and then at some point here turns around and goes back to the left. If this distance were more than 5, she got wet because she went into the lake. Or perhaps there's a bridge there or something. Okay, so when is she farthest from the lake? Well, that's going to be here at the very end of the trip because she's going to end up further away. So how do we find that? Well, if we integrate from 0 to 1, this function, this velocity, we will get the total difference we'll get the change in position, which is going to be negative. We have to add that to -5 to see how far away she is. So what we're doing is we're taking a -5 plus the integral from 0 to 1 of v of t dt, absolute value of that. Now I get that integral to be negative 8.3 added to 5 is negative 13.3 is her position, so that puts her a total distance of 13.3 miles from the lake. How did I get negative 8.3? Well, I basically divided this up into little rectangles. So I drew little rectangles. I'll draw one of them perhaps for you here. And maybe I drew a little rectangle like that. That's a little bit too low, too high. Maybe I need to go a little lower. How do I know it's too high? I want this area right here to match this area right here. So I would do that on each particular one. A little high, a little lower, and so forth. And this, I can find the areas of these rectangles and add them up. Some of them, the ones that go above, we'll add to the integral. And those that, for example, when I get down here and draw it maybe something like this, and maybe a little higher, something like this, then I do the opposite of this area for a negative value added to the integral. Just erase those pictures. Yeah. Okay, so that's what I got when I did it. You can estimate it yourself. Did she reach the lake? If not, what happened? Well, the closest she got to the lake was here at 20 minutes into her trip when she turned around. So we just need to do the integral on this piece. Again, I can draw some rectangles and just do on that. And I find that area to be approximately 1.5, and it went to the right. So she started at negative 5. We add the integral from 0 to 1/3 of v of t dt, which is that 1/3 is that x-intercept at 1/3 comma 0. And then we integrate there, and I got about 1.5. That 1.5 represents this area right here. So she went 1.5 to the right, and that's as close as she got, which is still 3.5 miles from the lake before she turned around and went back the other direction. So she ends up 3.5 miles to the left of the lake at negative 3.5 on the coordinate system here, 1.5 miles to the right of where she started. Then she goes back to the left. At some point she ends up back where she started. That's going to be in here somewhere. And then she ends up even further away, about 13.3 miles from where she started. Alright, here's another example. We have the velocity of a particle moving along the x-axis described by the formula v of t equals 5t cubed minus 7. The particle starts at the origin at time 0, and we're going to approximate some values here. So we can use numerical integration if we want to, for example, if all we need is decimal values. So here's a graph of the function. Here's kind of a close-up at the beginning. Notice it starts at time 0. It's negative velocity, so we're going to the left. The particle is actually just moving. If we had a horizontal axis here, like the x-axis here, starts at the origin, it starts moving to the left. Then it turns around at, looks like about 1, not about 1. Anyway, close to 1, but some value there, whenever this is equal to 0. I guess it's the cube root of 7/5, whatever that is. Then it turns, at that time it stops, turns around, it goes back to the right, and then it just keeps going further and further and further to the right. Okay, it's kind of like the bicycle problem that we just did, except we're just given the formula for the motion here. So the total distance the particle moves is going to be absolute value of the velocity to get a speed, and we integrate that speed over the time. So from 0 to 15, we get the absolute value of that. So this time we don't care whether they're going right or left. We're going to add how far we go to the right, left, plus how far we come back to the right to get to 0, and then how far more we go to the right. We're going to add all that together for the distance. If the little particle was like a car, for example, and it had a odometer, and it kept track of the total distance traveled, this is what it would read. And if we integrate that, I just did it with the function integrated on the calculator, I get about 63,188, whatever our units are here. The net distance it travels is, you integrate the velocity first and then take the absolute value. So if you integrate the velocity from 0 to 15, we get 63,176.25, which is the position to the right. And then, of course, take the absolute value. It doesn't change. It's still that far from 0. Notice that that's a smaller value than the total distance traveled, because this only counts where we ended up, how far that is to the right of 0, whereas the original one counts all of that, plus how far you went to the left twice, because you went to the left and you went back to the right just to get to 0. It counts that. Okay, and in terms of an area, this area right here above the curve and up to the axis is balanced by some area to the maybe just 1 or 2 couple units over under the curve is balanced out, and then the area from there on over under this curve is this total value here. But if we add all those areas together to the right and left here, above and below the axis, then we get this first number. So this is just measuring how far we are from our starting point. So total distance traveled, you absolute value first, then integrate. Absolute value of the velocity, then integrate. And the net distance is integrate the velocity, then absolute value. If you want the actual change in position, no absolute value, could be positive or negative depending on whether you end up to the right or left of the point where you started. Acceleration is the derivative of the velocity. So if we take a derivative here, we get 3 times 5 is 15. It goes down to the second power. Here's the 7, negative 7 is 0. So it's just 15x squared. The position, which is just an x value on an x axis, so we might as well call that x of t, is the integral of the velocity of t, or the antiderivative. So we just take the antiderivative here, which is, let's see, the power goes up 1 to 4, divided by the new power. So that's 5/4 t to the 4th. This negative 7 gets a t with it, and plus c. And then to find the c value, we need to plug in one point we know. When we know at time 0 was at the origin, so x is 0 when t is 0. And so we plug in that, and we see that c is also 0. And so x of t is 5/4 t to the 4th minus 7t. Let's do some more problems like these last couple of problems. So we're going to start with an initial value problem. Here it is. And we're going to work through this. So that when the brakes are fully applied, a certain automobile has a constant deceleration. Okay, acceleration in the negative that direction, or it's decelerating, at 23 feet per second square, and it has an initial velocity of 90 miles per hour. And so if we go out and see a skid mark where he's first applied the brakes, we can mark that position as 0, and the direction of the skid of the car, let's call that positive. Okay? So notice we have a constant function for the acceleration. And so here are some of the questions that we want to ask. What's the formula for the velocity of the automobile as a function of time? And we could say, what's the formula for the acceleration as well? What's the formula for the position of the car as a function of time? In other words, the distance from the beginning of the skid marks. How long did it take the car to come to stop by the time once he applied the brakes? And how many feet will it travel during that time? Okay. Now notice in this particular example, we know the initial velocity of the car, and we should know, so this allows us to find how long it's going to take for that car to stop. We could also work this kind of a different order here. If we knew the length of the skid mark and we knew the rate of deceleration for the car, we could solve for that initial velocity. And this is one way, like a policeman might look at the skid mark and tell how fast the car was going when it applied the brakes. So the thing that we want to know is the derivative of position. The derivative of the distance is the velocity or speed, and the derivative of velocity is acceleration. So if we start with position function, we successively take derivatives between velocity and acceleration. However, here we're starting with the constant acceleration, so we take antiderivatives to find velocity and another antiderivative to find position. So we'll let t represent the time in seconds from the times the brakes are applied, and let S represent the position in feet with S of 0 equals 0. Now we're told at the time the brakes were applied the velocity is 90 miles per hour, but we want to get things in terms of feet in seconds, not miles an hour. So we just do a little unit conversion here. 90 miles per hour times 5,280 feet is 1 mile. 1 hour is 60 minutes, 1 minute is 60 seconds. And if you notice the way I've got this arranged, the miles cancel, the hours cancel, the minutes cancel, and we're left with, see, the only thing left is feet on the top and second on the bottom. And so you multiply on your calculator 90 times 5,280 divided by 60 divided by 60, and you get 132 feet per second, which is the velocity of the car. That is 90 miles per hour. It's just written now in feet per second, different units. So we take the direction the motion of the car is positive and the acceleration is negative, so it's in the opposite direction. In other words, the car is slowing down. And t is the time in seconds since the brakes were applied. And we have the acceleration function is just negative 23, right? Was that the, yeah, that was given to us here. It's a constant, so it's just a constant function. So the antiderivative will just be a linear function. V of t is negative 23t plus c1. If you plug in 0 for t, we get, this goes away, you get 0. So c1 is, well, v of 0 is 132 in the positive direction. So 132 is for the v when I put in t is 0, and we get c1 is 132. So v of t is negative 23t plus 32, and that's going to be in feet per second. Now we take another antiderivative of that to get the position, which I'm using the letter S for that. Okay, so let's see, this goes up to power 2 divided by 2, so it's negative 23 halves t squared. This picks up a t plus 132t plus c2. So if you take the derivative of that, you get what's in the parentheses up here. Now we know the position at time 0 is also 0, so we plug in 0 here and we get c2 is also 0. So S of t is negative 23 halves t squared plus 132t, and that's the position in feet from where the brakes are applied. At some point the car is going to stop, and so that the velocity will be 0, and we can see that that happens. If you look at the solution here, you add 23t to both sides and divide by 23. T is 132 over 23 seconds, or in other words approximately about 5.7 seconds. At this time, the position is S of 132 over 23. So you take this position function here for S and just plug that number in, work it out, and it's about 378.8 feet, about 379 feet. So the car will take about 5.74 seconds to stop, and it's going to be, and during that time, it's going to travel 379 feet. So a car traveling at, if this is the appropriate constant deceleration for that car is 23 feet per second square, then a car traveling at 90 miles an hour better leave a reaction time of about 5.74 seconds and between whatever's in front of it, so that it will, once it puts on the brake, it's going to take another 379 feet to stop. You want to stop before you hit something, so you need to leave at least 380 feet, and this is not accounting for reaction time, so you're going to have to leave more than that. So it's a fairly realistic problem, but this amount of deceleration here is going to depend on the quality of the tires and a few other factors, but it's basically the friction that's generated by that. So there are a couple of motion type problems, and we'll look at some average value problems in the next